Hopefully you can all see the screen. So today we start with chapter 1. I will try to keep sync with the other section as well. So previously I was able to complete only half of this lecture, and that's fine. So I found a nice place to break within the lecture. We'll go up to that part. Okay. So to start, obviously, since this is officially your first class in telecommunication, many technical lectures, right? We try to formalize layman's definitions. So here, the word telecommunication has no formal definition. The formal definition is what we would mean in general English language, means communicating from a distance. If I look back, or if you look back, right, the first instances of communication were probably using pigeons in the 1600s, right? Homing pigeons, sending letters through pigeons. First instance of what would be telecommunication would be the telegraph in the 1800s. Have you all heard of Morse code?
Yes, sir.
Yes. Has anyone not heard of Morse code?
No.
Is there anyone who has not heard of it?
Sir, I didn't hear about it.
Okay. So it's anyway. I'm going to try to explain. If anyone who has heard of it, feel free to help me explain it. So it's, you know what a code is, right? It's a representation of data. So Samuel Morse, I think it was around the 1800s. I have to look up the exact date. He made a representation of all the letters and all the numbers using two symbols, a dot and a dash. So A to Z and 0 to 9, each of these symbols has a representation using a combination of dots and dashes. And S is 3 dots, and I think 3 dashes. And O is 3 dots. And E is 2 dots. With a combination of dots and dashes, and using between 1 to 4 of these, he had a representation of A to Z and 0 to 9. And then using dots and dashes, you could transmit messages wirelessly. Sort of the way the first telegraphs went were, railway lines. Imagine the railway lines. If you tap on one side with a hammer, like this, this noise would carry a long distance, right? And with a homemade, like a cone acting as a speaker, you could pick up this noise kilometers away. Okay. And then the coding was made in such a way that 2 taps would represent a dot, 4 taps would represent a dash. And then a dot and a dash, a combination of dot and a dash represents every symbol. So you could actually transmit a verbal message. Does everyone get it?
Yes, sir.
Yeah. Okay. So this was actually how telegraph worked, and was actually the first instance of telecommunication.
So telegraph was basically Morse code.
Say it again.
Telegraph was basically Morse code.
Telegraph was basically Morse code. Yes. There are other, actually current day also there are uses of it. Do you know how ships signal one ship to another? Have you all seen flashlights, torches?
Yes, movie to
Torches have an on-off button, and you notice it has a tap button as well. If you tap, is a blink of light.
Yes, sir.
Yeah.
They communicate with the watchtower with the lights.
Sorry?
They communicate with the watchtowers with the lights.
Exactly. With the tap, 1 tap, or I think 2 taps, just one can be mistaken. 2 taps represent a dot, 4 taps represent a dash. So exactly, lighthouses with flashlights like that can actually communicate full messages. And people who work in Red Cross, in lighthouses, they're supposed to have the Morse code memorized to quickly decipher. Okay, so obviously, modern day communication is different methods. We use voltages, right? Analog to digital conversion. 5 volt is typically a 1. So first, data is represented in 1s and 0s, and then communicated through typically transmission media. There are typically 3 kinds of transmission media. Electrical, which is copper wire of all kinds, right, where it's electrical signals that transmit. Optical fiber, right, where electrical is converted to optical pulses, right? So then optical pulses carry the information. and then in using electromagnetic waves in wireless medium. So within wireless, written here vacuum, typically it's precisely vacuum only in satellite communication where you communicate to a satellite. Within the earth, it's not vacuum, it's through the air, right? But it's, for practical purposes, it's similar. So that is the wireless method. And then there is the optical fiber, and then through actual electrical wire. Okay. Before we go along, another statement about the textbook. So previous class I mentioned, right? This book is a layman's book, and the objective of the class is to give a brief, not really an overview, right? An introduction to pick out bits and pieces of the formal class, so that when you go into the formal class, you come in with some general knowledge of it. Okay. Because this book is written also as a general knowledge, from a general knowledge perspective, the author uses some terms which are his own, and uses some definitions and some divisions. I'll give you example, which are his own. So as we go along, some of these cases I will introduce the formal technical terms, right? The professional terms, and then also the distinctions that the author makes. Some of them are his own. For those that are his own, I will not ask you direct questions. Those that are formal distinction, I could ask you direct questions. The first example is like here he has said the effectiveness of a communication system is based on 4 fundamental characteristics. So this separation into these 4, this is this author's himself. You see what I mean? The terms are not his. So on this, if I ask you a question, I will not ask you what are the 4 effective methods. I may ask you what does delivery mean, what does accuracy mean. Do you realize, get the distinction? I could ask you what does jitter mean, but I will not say what is the 4 way of judging a communication system. Because these 4 ways, this is the way he has divided, right? But once again, since it's an introductory book and since we are following him, we can follow his method. It is a good way of learning, right? But it is not the formal separation. Okay. So here also his third term, he calls it timeliness. The formal term is delay. So I've introduced this term because this is not a very difficult term, and let's learn the professional language. Okay, so let's, once again, since we are following the book, let's follow the author's method of learning. So he has divided a communication system into 4 ways of judging the quality of a communication system. First is delivery. So for a system to be effective, we need the data to be delivered properly. And by properly, what it means is it must deliver the data to the correct destination. Correct means to be received by the intended user and only by the intended user. So this means in this class we have 30 students registered. So this lecture must reach all 30 of you and exactly these 30 of you, right? So that is what delivery means. So you receive an intended user and only by that device. So it's very obvious, but right, when you define, you have to include, right? To make the definition concrete. Okay, delivery options. These 3 are standard definitions, and that's why I've mentioned it. So there are 3 ways of delivering: unicast, multicast, and broadcast. And once again, this is a standard technical separation and standard technical terms. Unicast means intended for a single target. Broadcast means intended for everybody. And multicast means intended for a subset. So once again, definition of broadcast is also context dependent. Okay. From IUB's perspective, broadcast must mean send a mail to everybody, right? Every subscriber. From the government's perspective, broadcast means a message shown on BTV, meant for every citizen. Okay. Unicast means to a single target person, and multicast is to a group. So from IUB's perspective, each class is a multicast group, right? And broadcast must be something to all students, all faculty, all staff. Okay. So you realize that, I mean, broadcast definitely is, when you mean to everybody, what is everybody is context dependent, but this is the standard separation. Okay. Also, the other thing I mentioned, right, after every slide, I will pause for a few seconds. If I don't pause, please remind me. Because once again, right, if I don't want to hear, if I lose you in the middle of a lecture, it's very difficult to go back. I cannot see you. Okay, everyone, please. Like I
Sir,
said,
I have a question, sir.
yeah, please.
Sir, we are doing now class, so this is called multicast, right? Like we are in a group and you are delivering as the communication system.
So from IUB's perspective, this is multicast. Then from the classes perspective, I could argue that a lecture is broadcast, and if I have consultation hours with subgroups of you, that will be multicast. Okay. So,
Okay,
but
sir.
the strict definition would be, yes, this is multicast, everybody at IUB is broadcast. But if I suppose I write a sentence, I will broadcast this to the class. I am grammatically correct and technically correct.
Sir, so this mostly changes with the perspective.
That's what this mostly changes with the perspective.
Okay, sir. Got it.
So you see, imagine here, right? Google Classroom may have an option, I don't know if it does, send a message to the entire class. So from a coder's point of view, it is very easy, right? You select everyone, select all. Basically, broadcast means select all. And multicast means pick and choose. Okay. Now, often when we change phone numbers, we send a broadcast to our entire phone book. And like you're saying, that is different from the government sending a broadcast to every cell phone subscriber. Okay. Because delivery, next is accuracy. Accuracy means the data must be delivered without error. Now, this brings to the point that every transmission is liable to error because of two reasons. Error means bits getting flipped, 1 becoming a 0, 0 becoming a 1. And every transmission is like, you cannot make error into 0. Every transmission line is gives a quality value based on the probability of error. Typically, it's in the order of 1 in a million, which means 1 in a million bits gets flipped. But you cannot make it 0. There are two avenues in which error creeps in. One is noise, the other is attenuation. This I have not put in the slide because this is the topic of electrical engineering and not exactly part of the syllabus. But for general knowledge and to understand the concept, you need a bit of side knowledge. So once again, right? One is noise, other is attenuation. Have all of you heard the two terms before?
No, sir.
So what is attenuation?
So not familiar with attenuation.
Has anyone not heard the term? I will explain, but have anyone never actually heard the term?
I didn't.
Okay. Noise, technical definition of noise is any unwanted signal. Okay. So imagine, have you ever tuned a radio? I'm sure you have, right? A radio receiver, what it does is it tunes to the exact frequency. Now, it cannot tune to the exact frequency. It tunes to the exact frequency plus minus some delta. And could be other electromagnetic noise, like when two wires are close together, right? If the actual signal goes in one wire, there's an induced current in the other. So that adds noise.
Sir, what's the spelling again? Add noise, or what did you say?
One is noise, other is attenuation. ATTENUATION. I don't even remember. Type it similar, it'll come up. I'll get to it. Wait. So once again, technical definition of noise is any unwanted signal. Okay. And usually when you transmit your signal, the way a receiver has no way of exactly knowing. He has no way of knowing which is the desired signal and which is the noise. He makes some guesses. And we have device systems in which the guesses are correct 99.9% of the time. So first way of guessing is typically your actual signal will be transmitted at higher amplitude. So anything low amplitude is noise, he filters those out. Typically, he's told the exact frequency, anything in other frequency is noise, right? But like I'm mentioning, if there are electrical wires close by, a signal flowing in a wire close by will have induced current in your wire. Every electronic device produces thermal noise itself. Okay, this is for electrical transmission. In an optical transmission, any ambient light, right? Any ambient light would be optical noise. Okay, and then, so this is the noise part. Okay, attenuation means signal loss. If you transmit an electrical signal, right, its amplitude will keep on reducing with the inverse square law. So attenuation is a technical term for loss just due to traversing a distance. Okay. In every medium absorbs, in an optical fiber actually absorbs a bit of light. So you've sent an optical pulse. If it travels, let's say, a distance from London to New York underneath the Atlantic Ocean, right? It will, every millimeter, it will keep on, the optical fiber will keep on absorbing a little bit of it. So now let's get to a real world scenario. Suppose you have transmitted a 5-volt signal as a 1 and a 0-volt as a 0. What will happen in the transmission medium is after a kilometer, noise will keep getting added to the 0-volt, right? And the 5-volt noise will keep getting added, and some of it will also keep getting absorbed. So a 5-volt pulse may be received as a 4-volt pulse. A 0-volt may be received as a 0.5-volt pulse. Do you see that? Do you see that can happen? Everyone?
Yes, sir.
Yeah?
Yes,
okay.
sir.
Also, a perfect 5-volt square wave will not remain square at the receiver. It will seem curved, right? It will not be a perfect 5-volt, because imagine 5-volt over 5 milliseconds. At every millisecond, the absorption is not the same. You realize that it will not be a perfect square wave either. Now, in this scenario, if a 5-volt becomes a 4-volt and a 0-volt becomes a 0.5-volt due to noise, a receiver is able to distinguish between the two. He'll see a 5. He knows that, sorry, he'll see a 4. He knows that a 4-volt was not sent. Either a 0 or a 5 was sent. When you see 4, it's most likely closest to a 5, right? When he sees a 0.5, he knows this is actually nothing was sent. This 0.5 is actually atmospheric noise. Okay? Now,
Yes,
suppose your line is very noisy. Suppose your distance is very far. With absorb, your 5-volt has now become a 2-volt. We keep on getting absorbed at every link. Suppose it has traversed through multiple links. Suppose a 0-volt has picked up noise along the way, it is also now 2-volt. Or it is also now 2.4-volt. So now the receiver is in trouble. He cannot be sure. Right? So in these cases, typically what a receiver will do is, he will try to maximize the probability of correct decision. He will say, okay, I will set a halfway mark, 2.5-volt. If I see anything below that, I will assume it's a 0. If I say anything above 2.5, I will assume it's a 5. And he thinks this is his best way of minimizing the probability of error. Right? But he cannot make it 0. And this is actually what is done. Now, what I'm saying is a transmission system must ensure accurate delivery, which is error-free delivery. And what I'm saying is 100% error-free is impossible. So then there are other methods that is used to correct. For next level is, suppose an error is detected. What will the receiver do? One, the receiver can ignore the error. It can present the error to the receiver. This is rarely done. Second, the receiver can just delete that information. This is often done. Imagine a case of real-time video transmission. cricket is restarting today after the pandemic, right? There's an England-West Indies test match at 4 p.m. Suppose you're watching a cricket telecast. A 1-bit error could mean 1 pixel error, could mean 1 frame error. A video is 30 frames a second. If it's high definition, right? 640 by 640 pixels in every frame. If 1 pixel is in error, if that pixel information is deleted, will the human eye notice it?
No.
Right? Most likely not.
No.
Right? So that is what is done. Next, now suppose my application is online banking. Suppose 1 bit is error. In this case, is it acceptable? No, right? No. So in this case, what you will do is you will ask the sender for a retransmission. The difference between, you could also do that in the video transmission case. You could ask for the pixel to be resent, but it is not worth the effort. So these are next level decisions you make, right? First, accuracy means it must deliver error-free. And then what I'm saying is 100% error-free is impossible. Every system gives you a probability of error. And depending on the application, the probability of error is minimized. Bank's final level check is every month you're supposed to get a bank statement and you're given 30 days to declare if you notice any error to inform the bank for the next 30 days. That is the final level check, right? Because even that, it could be 1 in a billion, but the error rate is not 0. Okay, so next is delay. Timeliness is this book's term. The actual technical term is delay. This means each system must deliver the data within some time bind. And the time bind depends on the application. For a real-time video transmission, you're okay with a 10-second delay. For an email, you're okay with a 1-minute delay. For a banking transaction, you could be okay with a 1-hour delay, right? I will not say it 1 day, because even banking transaction, for credit card transmissions, you're okay with a 1-minute delay maximum. And for online gaming, you are okay with probably a millisecond delay, right? So what I'm saying is delay matters, and each application has, obviously delay cannot be 0, right? Even speed of light is high, but it is not infinite. The delay cannot be 0, but depending on the application, there is a limit, and the system must deliver within that limit, and data delivered later useless. Imagine online gaming, right? Here even millisecond delay is useless. Real-time transmission, once again, delivered after that frame has been presented is useless. So your real-time transmission also has some requirements, delivering data as they are produced error-free in the same order that they are produced. I'll explain this in a minute. And without significant delay. Okay, same order. So network packets, all of them do not also follow the same route. Are you aware? Suppose different frames are put into the transmission line. There is not one link between the sender and the receiver. There are multiple links. Right? Are you aware of that?
Yes, sir.
Yeah. So each packet may take a different route. And it is possible that packet 3 arrives before packet 2. So in real-time transmission, you have to deliver in order, right? In the correct order. A lot of video players have this buffering because of this reason. If it buffers in the beginning, you are okay with it. If it buffers in the middle, the viewer is annoyed. So in the beginning, what the buffer tries to do is wait for 10 packets to arrive. It is possible packet 10 might arrive before packet 2, right? But once 10 has arrived, he will start then presenting packet 1, then packet 2, then packet 3. And he hopes that by the time the 10th packet is presented, packets 11 to 20 will have arrived in whatever order. So then he will present 11. And then initial buffering, how long he will take, the player must determine how disordered the packets are. Is it 1 or 2 packets that are disordered? Just 3 arrives before 2, but there's no chance of 10 arriving before 2 and 3. So he can just have a buffer of 2-3 packets. If packets are coming in completely randomly, maybe packet 100 has arrived, and then packet 50 has arrived, and the packets 1 to 49 are missing, then he must make sure he has packets 1 to 500 before he starts playing. You realize that? And often you've seen Netflix, right? Your video speed keeps increasing after the beginning. Initially, you don't get high definition, but it ramps up because your player is also trying to learn your system, right? How many bits are flipped in your system? How slow is your system? How many data per minute can your system process? And how likely is it that packets arrive in order? And then he will make the decision how big a buffer it must locally store in your machine before it starts displaying. Okay? Okay. Next term is also related to delay, but completely different meaning, called jitter. This means the variation in the delay. Let's go back to the previous slide. Let's say I have, does everyone know the difference between average and standard deviation? Sigma.
Yes.
Does anyone not know
Yes,
what
sir.
standard deviation is?
Sir, I don't know.
Okay. Have you never heard of it or have you forgotten? It's either answer is fine.
I heard of it, but I forgot.
Okay. Is there anyone who has never heard of it? Okay. So average, what average means is very obvious, right? Average or mean. It's the central value. Standard deviation is a measure of the variation. Easiest way to explain would be by an example. Let's say we get 3 packets. Okay. All 3 packets arrive after 10 milliseconds. Then what is my average? Obviously 10. Okay. Second case, suppose first package arrives after 9 milliseconds, second one arrives after 10, third one after 11. In this case, what is my average? Again 10, right? 9, 10, and 11. Third case, suppose first packet arrives after 5 milliseconds or seconds, whatever, after 5 units. Second packet arrives after 15, third one after 10. Third case also, what is my average? Again 10, right? Is everyone with me? Right?
Yes.
Right? Explaining 3 possible cases. All 3 arrive at 10 seconds. At times 9, 10, and 11. At 5, 10, and 15. Or maybe 5, 15, and 10. But are the cases the same? Right? They're not. Right? The third case is more of a problem. So the standard deviation measures this variation from the mean. Actual definition is it's the average of the mean difference, the difference from the mean. Now, first case, all 3 are 10. The standard deviation value is 0. Second case, 9, 10, and 11. So the differences are +1 and -1 and 0 from the mean. Right, everyone? Third case, differences are -5, +5, and 0. So it's the average of this. Now, in terms of a technical detail, if I actually take the average of -1, +1, and 0, the average is also going to be 0 because -1 and +1 will cancel out. If I take the average of -5, +5, and 0, will also be 0. But we know, that the third case is different, right? So the formula has been designed in such a way that what you do is first you square the differences, okay, so that the negative also becomes a positive. And then you average, and then you take a square root of the average. So the actual formula value would be, you take -1 square is the first case, standard deviation is 0, all 3 zeros. Next case, -1, 0, and +1. If you square them all, it's 1, 0, and 1. So the average is 2 by 3. Standard deviation is square root of 2 by 3. Is everyone following?
Yes, sir.
Third case, -5, 0, and 5. So you square, it will be 25, 0, and 25. So the average is 50 divided by 3. And standard deviation is square root of 50 by 3. So in this ways, your metric will give a high value in the third case. And jitter is the standard deviation in the delay. And so this measures the variability. And in video, so this is why jitter value matters more than the average value. than the delay value. Because the delay average means you wait that much of time and then you start playing back. Now, jitter means you have to wait some extra, right? And there is more uncertainty. In a separate application, values of stocks are judged by the standard deviation of their values, not the average. Because the standard deviation measures the risk associated with that stock, with that company. If a company gives you a high profit this year, but a high loss next year, that means that stock is more risky. Versus if the separate company gives you the average profit every year, that stock is safer. And a standard deviation in stock prices is measured as the value of the uncertainty or the risk associated with purchasing that stock. And typically, if different stocks have the same average, actually this is a formal law in investments. If stocks have a similar average, you're supposed to pick among the average, you're supposed to pick the stock with the lowest standard deviation value, because that is the lowest risk. And on the other hand, if you pick a high standard deviation, you must make sure that the average value is multiple times the other stock value, which has lower standard deviation. So that means if you have high risk, your possibility of return is also proportional to that risk. You see the point? My undergrad was a physics and economics double major. So a lot of the applications of these, and I mean, it sounds very separate subjects, but a lot of the math is actually similar if you study those subjects mathematically. Okay, so are we okay with this? All four values here? Anyone? Once again, now in the pandemic, we all watch Netflix a lot, right? Jitter is the. Has anyone heard this term before?
Yes, sir.
Okay, that's good. So now you know the technical meaning. Okay. How are we doing for time? About 1:20. Okay. Does anyone need a break? Everyone okay? Drink of water? You need a drink of water? Go a bit more. I was expecting online to be faster because last class I mentioned, right? We have 20 minutes extra time, no need to wait for attendance. My experience in the previous section has been is the other way around. Because I cannot, get an acknowledgement from you, I have to try to explain in multiple ways and slower than I would do in a physical class. Okay, next, once again, according to this author, or let me phrase it in this manner. This author has separated the components in a data communication infrastructure into 5 components, into 5 categories. First, the message, which is the information to be transmitted, right? Popular form of information, the categories we use are text, numbers, images, audio, and video. Text and numbers, I guess the difference is text is a string. Numbers, if you want to do calculations, for CS people, you know the difference between representing a number as a string versus as a number where you do calculations. If you have done digital logic design, you've all done digital logic design. Text representation is the ASCII or Unicode representation, right? And numbers is where you would actually would be a what's the word? How do you represent negative numbers? Forgotten myself. 2's complement, right? So it would be that way of representing, so that you can do calculations. And then images made up of pixels, audio files, and then video, which is actually a sequence of images. So this is the message to be transmitted. Then you have a sender, which is the device that will transmit. Modern day, it can be any IoT device. It can be an olden days, right? I mean, we still use it. It can be a landline telephone handset. Okay. Video camera is an example. If it can transmit, it would be an example of an IoT device. Now, with mobile phones, very few people buy actual digital cameras, right? And only that's why essentially all cameras will allow memory cards to wirelessly transmit will connect to a LAN. Okay. And then this is the topology diagram. So you have a sender on one side, you have the receiver on the other side, and you have the transmission medium in between. And this medium here, obviously we have drawn a line. It can be an electrical wire, it can be an optical fiber, it can be a wireless channel. Right? And then we have the sending message by the sender application, which will go to the receiver application. That's what the protocol means. So then the receiver is that receives the device. It can be a telephone handset or it can be a television, right? And the transmission medium is the physical path by which the message travels from sender to receiver. And like I've said, there are physically three kinds of media: electrical wire, which can be subdivided into twisted pair, category 5, category 3, coaxial cable, right? Fiber optic, and then the air or vacuum. Right? So this is okay. Next term we'll have to learn here is what is a protocol. So we've all learned basic classes, right? The first thing you learn in a CS class is what is an algorithm, right? A step-by-step set of instructions that your processor follows. When you do computer architecture, you learn assembly language. Have you all done computer architecture and microprocessor?
Yes, sir.
So you're all
Yes, sir.
Yes, sir.
aware of the
Yes, sir.
of the right. So you know what the assembly language is, right? So your hardware essentially it does implements every step. Now, in a communication infrastructure, a separate problem arises. Here, you have two nodes that are virtually interconnected. In the sense, your steps that you do in the first node, in the sender, is a function of the steps in the receiver. As an example, and suppose we're doing online banking, and suppose, like I mentioned, that your bits may be in error. And the decision you've come to is in this application, if a receiver receives a packet wrongly, you will ask the sender to have it resent. Okay? So now the sender, once it has sent packet 1, it must ensure that the packet 1 has been received correctly before it can send packet 2. Which means it must wait for the receiver to send the acknowledgement. And then the receiver might say he has received the packet correctly, in which case he will send packet 2. Receiver might say he has received the packet wrongly, in which case he must resend packet 1. So the algorithm at the sender end is not standalone, right? So here the term protocol comes in, which means it's the algorithm of the entire interconnected system. For our class, we have decided on a protocol. We first needed to decide on a protocol. Two things we could have done. When I present, how do I take student questions, right? There were two methods we could have decided upon. First, I could have said, I will finish the lecture, you will write down and hold all your questions. At the end of the class, I will go through your attendance list one by one, unmute you one by one, attendance wise or alphabetically, and you will ask your questions. So one method we could have adopted. Other method which we did adopt is while I go through the class, you're welcome to each of you interrupt me. If you interrupt, I will stop presenting, I will listen to you, answer the question, and then I will move on, right? So these are examples of two separate protocols. So first, we needed to design a protocol where we would be able to have effective communication. Then we needed to make sure we all understood the protocol. I needed to have communicated the protocol itself to all of you. And then made sure we all understood it. And then made sure we all agreed to it. Right? If one of you thinks you do not agree with my protocol, the system will not work. One of you thinks no, you will wait till the end to answer. But at the end, maybe I will close down the session, and you will not be able to answer. So first, right, you see my point? I needed to communicate the protocol to all of you, make sure all of you have understood it, and also make sure all of you have agreed to it and are abiding by it. So this is what a protocol means. It's the equivalent of an algorithm in an interconnected system. So set of rules that govern the communication represents the agreement between the devices. And there's an example from a book that if one person speaks French and the other speaks Japanese, they cannot understand. So two devices may be connected but not communicating. So our example would be, right, if one of you thinks you will ask me a question at the end of the class, but at the end of the class, I don't give you time because the belief I have is all of you have understood and agreed, and you will ask in the middle of the class if you have a question. Okay. So, yes, please. Exactly. That's what I'm saying. Both of them must agree, and then first they must be all told of the protocol, that they must agree on it, and they must also be able to implement it. The technical case, yeah, good, go ahead. It is, exactly. That's what I'm saying. It's the equivalent of an algorithm. Suppose we decided you will ask questions at the end, right? Suppose, as a technical analogy, suppose one of you does not have the buffer, or one device does not have the buffer to store, then that device will not be able to abide by this protocol. So either the protocol must be changed or that device must be taken offline, right? Because the system will fail. So like you say, the set of rules, it's the equivalent of an algorithm in an interconnected system. Whereas an algorithm was only in a standalone system. Okay. Next, how to represent data. So once again, they're all obviously eventually converted. Go ahead.
Deciphering get protocol.
Could not hear too much noise. Again, please. Do you want to write down the question in the chat box?
Sir, the cipher and decipher.
Maybe you can write the question in the chat box briefly. Go ahead. I don't see a question. No need to be shy. Cipher and deciphering. Okay. Yes, exactly. Exactly. So here, so this question is, does encryption and decryption, right? Is that part of a protocol? Exactly. So here, sorry, how did I get to the other slide? 1 second. Okay, so exactly. So both sides must agree on the cipher algorithm as well, right? And first, exactly, you must be told that the text is ciphertext. Otherwise, the receiver will present the ciphertext. It will not work, right? Okay. So first example is the fact that it is encrypted communication. Next, the encryption algorithm must also be understood. The receiver must have the correct decryption algorithm to be able to decrypt the message. The cyber key. Okay.
So like
next is
it's like
go ahead. Yeah.
So it's like, for example, like Bcash then. Like if I'm
Bcash.
sending a money to the like Bcash. Like I'm sending money, it's encrypting, and over there it's reaching the receiver and it's decrypting.
Exactly.
Right. So,
Exactly.
yeah.
Got it. When you log into your email, right, all passwords are encrypted. Okay. So let's get into data representation. So text is the easiest thing to represent, right? Now the first set of code was ASCII. You all know of ASCII, right? In DLD, that's what we teach. 7-bit representation, right, for each letter and each number. And initially, the English keyboard has 101 keys. So 7-bit has 2 to the 128, 2 to the 7, sorry, equal to 128 possibilities. So that was enough for all English letter language, I mean, the entire keyboard, space bar and functions and everything. So next, it was expanded to 32 bits. And, this goes up exponentially. So 2 to the 32 is like a million. So the 128 bit would not have been enough for Bengali, right? With 52 short borno, Banjan borno, Juktakhar, everything, it goes beyond 100. If the English keyboard is 101, that goes beyond 128. So Unicode 2 to the 32 has a million. So that has all, essentially, you're aware of Unicode, right, everyone? Not just, it has a symbol for every language in the world. Imagine the Chinese language will be, with their different millions of characters. Now we probably have more than 128 emoticons. So all of them have a Unicode representation. Numbers, so numbers are converted into binary and 2's complement binary so that you can do the mathematical operations. And when it's represented as a string, that's when it's represented by Unicode. And difference between these two should be obvious now. Images. So images are eventually every images. So it's converted into different. It's separated by different pixels, right? A pixel is different squares. So everyone knows what a pixel is. A matrix of pixels. The first image representations were 48 by 64 pixels. Now in high definition, you have like 1,000 by 1,000. So that's the number of different squares. And obviously, the smaller a square, the higher the resolution. And you cannot pick out the difference in the human eye. And then each pixel is represented by an RGB value. Is everyone aware of that? The three primary colors, red, green, and blue. Because using a combination of these three, you can make any shade. Then the first images, each R, G, and B were given 7 or 8 bits. So 2 to the 8, 256. So there were 256 shades of red possible, 256 shades of green, and then blue, and which gave you 256 cube different shades of colors. And now even each pixel is each RGB primary color is at least 16 bits. And 2 to the 16 cubed becomes a million shades. So you really have every possible shade represented. Okay? And then here another thing I'll mention at one more slide. So I hope a lot of this, I'm not going too fast, right? A lot of it is still general knowledge. I'm giving you some bit more technical details or formalizing your technical detail. Audio is obviously just audio, sound, or music. So here, even connecting with images, a point I need to make is the real world is analog. Human senses are analog. And all communication starts with an analog, taking a picture of an analog world, right? Converting it to digital, transmitting it in digital, and then reconverting to analog because human senses are also analog. Human eyes and ears are also analog. So the obvious question is, why do you convert to digital? And the answer is digital has lower, many different reasons. I guess in an electrical engineering class, I would go more into detail, but here just for curiosity's sake, digital has is less susceptible to noise. An analog signal is more susceptible to noise. In a digital signal, it is easier to remove noise. It is easier to identify and remove noise. In an analog signal, that is not possible. Okay, and then also data compression is easier in digital. Ciphering and deciphering, encryption is easier or possible in digital. Okay, so that is. But the point to note is when we take a picture, any information from the real world that we digitize, the real world that we convert to or that we want to transmit, the real world, we're taking pictures, a snapshot of an analog world. And then once again, to the human eye and ear, we need to present in an analog fashion. Okay, and the way these conversions are done is the topic of DSP, digital signal processing. Okay, video is a set of images. Typically, video quality by definition means 30 frames per second. High definition can be more like 300 frames per second. So here again, the point to note is as your quality goes up, right, your bandwidth requirement goes up. If you have 30 frames a second, each frame has 640 by 48, just giving the basic numbers, 48 by 64 pixels. So that many number of pixels. Each pixel has RGB, 3 values, each with 8 bits represented. So imagine, and if it's 30 frames every second, so imagine the number of bits every second that must be transmitted for basic video. So now we can do a lot of sophisticated techniques have arisen where we can transmit high definition video even over a medium bandwidth line. Reasons are data encryption. Data compression. There are ways of compressing and then decompressing at the receiver. Okay. And here also there are two kinds of compression. First, there is something officially called lossy compression, something called lossless compression. Lossless means the compression algorithm is exactly reversible. All the fidelity and detail can be recovered at the receiver. Lossy means you are doing some averaging at the transmitter, you are actually reducing the quality. You're taking 4 pixels together and averaging out and sending one value of 1 pixel instead of 4. And this is done in case of where the exact fidelity or image quality is not that important. Your Netflix is primary example. Netflix might transmit at high definition, but every receiver's home band line is not at the same speed. So your home player will transmit at the level your player is. And here, right, if it's of 300 frames per second, if one person gets a 30 frame per second, your human eye will not judge the difference, will not be able to see the difference in the video quality. Okay, everyone with me here? Just a little bit left. Yeah. So let me pause again for 5 seconds. These two data representation details. Please think about it, go through back and forth in the slides yourself. We don't have that much left, so take 2 minutes. Any so just these two, how data is represented. And once again, all these are explained in detail in the textbook. I'm explaining in real time, right? Or I don't memorize the speech with the author or anyone. When you write, you have thought about it, you've had more time to write it. So that's a better thought out answer. So please read the book as well. And once again, I mentioned in the last class, right? I don't know if I mentioned here on the previous section. A result from psychology is that for just human beings, after every class, people will remember 90%. You will understand 90%, remember 90%. Next class, you will recall 50%. In a week, you will recall 10%. If you read the book at least once, just once after every class, after the week, this 10% will be increased to 50%. After the one class, this 70% will be increased to 90%. Just reading it once has tremendous improvement on human psychological ability to retain. So, I'm not saying this just to make your life hard. I'm saying it because scientifically it has been proven that just reading one more time does tremendous gains to your cognition ability, recollection ability. Okay, next slide. This is once again we saw unicast, multicast, and broadcast as the standard definition of the type of transmission. This is again a standard definition in the field. There are three ways of transmitting: simplex, half duplex, and full duplex. Simplex means the transmission is unidirectional. The example of this is your home television, your home radio. The tower transmits to you, you cannot talk back. Half duplex means it is bidirectional, but not simultaneously. This is an example of a walkie-talkie. Are people aware of a walkie-talkie?
Yes.
Is anyone not aware of a walkie-talkie? It has an over and out button, right? When you press that button, it will transmit from you to the other end. The other person can talk, but that information will not be transmitted back. And that's why you take turns, human communication, human protocols, right? The etiquette is to talk one at a time. You talk, you wait for the other person to finish, and then you talk, right? Usual human etiquette. So a walkie-talkie technically forces that. So that is called duplex, means both directional, but half duplex means one at a time. And
So two-way walkie-talkie কিভাবে কাজ করে?
One second. The way this is done is the channel is given to each person in turns. Yes, go ahead.
Sir, two-way walkie-talkie কিভাবে কাজ করে এই ক্ষেত্রে?
আবার বলো।
Two-way walkie-talkie কিভাবে কাজ করে এই ক্ষেত্রে?
I mean, two-way মানে হচ্ছে ওই যেটা বললাম যে it will transmit one direction at a time. মানে ওই একটা বাটন থাকে, ওটা প্রেস ওভার এন্ড আউট বলে, যে ওটা ওভার বলা মানে ওটা তুমি প্রেস করছো, তুমি প্রেস করে ধরে, ওটা করতে হয় কি প্রেস করে ধরে কথা বলতে হয়। সো ওয়ান্স ইউ হোল্ড ইট, তখন দ্য চ্যানেল, মানে you have been made the transmitter, the other side has been made the receiver, and the channel will transmit from you to the other side. If you leave it, the channel is turned off. So ওই ছাড়ার আগে ওই জন্য the walkie talkie human protocol is when you leave it you say over, which means you're leaving the button, and the other side will then hold the button. So অন্য side hold করলে তখন আবার the transmission medium will transmit from the other side to you. আর কেউ হোল্ড না করলে the transmission medium is actually turned off. দুজন একসাথে হোল্ড করলে মানে যে আগে মিলিসেকেন্ড আগে বাটন প্রেস করেছে ওইটাই হবে। ওকে, আর আউট বলা হয় যখন বলতে যে ওকে ইউ আর টার্নিং ইট অফ, কনভারসেশন ইজ ওভার। সো ওই জন্য মানে ওয়াকি টকি কার্টেসি ইজ হোল্ড করে কথা বলে ওভার বলে তখন ছাড়তে হয়। ওকে, এটাই জানতে চাচ্ছ নাকি ডু ইউ ওয়ান্ট নো দ্য টেকনিক্যাল ডিটেইল?
Yes, sir. Little technical detail.
দুই সাইড থেকে একবারে কথা বলে দেন, how will it done?
In a half duplex system, মানে definition of half duplex is দুই সাইড থেকে একসাথে কথা বলা যাবে না। You cannot, the data will not transmit in both direction at the same time. It will transmit because the entire channel will be given to one person. Entire channel has a bandwidth. That full thing will be given to the transmitter to transmit to the receiver. Versus full duplex means both at the same time. এখানে যেটা করা হয়, actually the channel is subdivided into two channels, one for each direction. Internally subdivided into two channels. So that is a telephone. Okay. So এখানে আবার মানে the points I'm trying to make are the three definitions. What does simplex mode mean? What does half duplex mode mean? What does full duplex mode mean? Right? And next, a walkie-talkie, phone, and TV যেটা দিলাম, these are examples. তুমি যেটা বলছো, if you have a walkie-talkie that allows simultaneous communication, then that walkie-talkie is a full duplex walkie-talkie, and is then technically more than a walkie-talkie. It's a phone. Okay.
Yes.
Okay. I think this is it. এখানে থাক। এই প্রত্যেক স্লাইডের এন্ডে I have written out the sections we have covered. So এটা because the whole thing was supposed to be one lecture, তাই না, মানে previous semester it was one lecture. Now in online setting it's taking longer, so I broke halfway. I did not redo the section heading. বুঝতে পারছো? So এখানে যেটা করতে হবে, you have to মানে you see my point, I have not covered all of section 1.1 and all of section 1.2, but এটা বইতে আমি আর ওই আমার স্লাইড আর চেঞ্জ করিনি। So আজকের জন্য you have to read through the book, and once again, since the slides are by the publisher, the slide headings follow the book headings, so you have to see what parts I have covered, right, up to data flow, and read that. কথাটা বুঝতে পারছো everyone? Yeah, okay. So up to data flow and data representation, this could be all of সেটাই আমি বলতেছি। এখানে এক্স্যাক্টলি কোন পার্ট আমি আর সেপারেট আরেকবার করে নিই আর কি, মানে নেক্সট ক্লাস শেষ হলে উইল ফিনিশ 1.2 পর্যন্ত। প্লিজ। IoT গুলা, IoT গুলা ওই ডিপেন্ডস অন দ্য IoT প্রোডাক্ট। IoT হতে পারে ইউজুয়ালি মানে আদার দেন আ টেলিফোন, usually you're not simultaneously transmitting and receiving, right, in most cases, telephone or video ছাড়া। So IoT products detail কি আমি জানি না, মানে আমি যেটা বলতে পারি হচ্ছে যে from the এই যে requirements because just IoT is a huge field, right? Each IoT product is obviously not doing the same thing. But for many IoT products, yes, it is a half duplex mode is more appropriate. That's it. Because most IoTs are not continuously transmitting or receiving, are rarely using the transmission phenomena, right? Are rarely transmitting. But IoT বলতে একটা ওই যেটা বললাম যে একটা ওই digital camera. এটা তো other than when you manually send, it has no need to communicate. Right. Does that answer the question? Okay. Anything else? আবার বলছি, there is no need to be shy. Unfortunately, ভালো হতো যদি chat box-এ it had an option of individually posting messages, right? Where if you are feeling self-conscious or feeling shy, you could post it. But please post a question if you have it. ঠিক আছে? And ওই যেটা এখানে যেটাই বলছি যে আমি হয় কি আবার লাইভ কিছুটা with experience of teaching, I can, or many people can look at a student and see that person probably has a question, and in class physically what I would do is I would ask that person after class. So I have no way of knowing that. I can tell you to email me individually, but that is also not a very effective or a productive and smart method, having to answer individual emails. So please বলে যাচ্ছে যে I have no way of looking at you and realizing that you have a question, you're being shy to say it, so you have to take the initiative. Okay guys, it's about 1:50. Yes, please. আচ্ছা, ওগুলা সবই full duplex. Those are all protocols that we will study in detail later on. That's it. Okay. Okay guys, enough. 1:50. Thank you. So once again, just parting thoughts is, please read please cover these parts in the book, and please try to acquire the physical book, and then ask me next class whatever you have not understood, whatever parts from today's class you would want me to repeat. A few slides quickly repeating, I don't mind. Okay. Because once again, we have not just me. I was speaking to Fedozait sir yesterday. He also had the same impression that we don't mind this semester, doing a little bit less. We don't mind taking a few less quizzes. At least let's try to maximize the learning as much as possible. Right?
So it's better.
Exactly. Okay, guys, have a good day. Bye. It's time for lunch.
Okay, sir.
Thank you, sir.
Bye, sir.
Bye.
Okay, thank you, sir.